We all year have been talking about intramolecular forces, these things. Now, we don't really use that term all that often, but an intramolecular force is a force between unlike atoms. All right, so it's like the bonds between atoms. An intermolecular force is a force between like molecules. So, for instance, an intermolecular force is the attraction between two water molecules. An intramolecular force is the attraction between the H and the O in this covalent bond. Chapter 11, we will focus on intermolecular forces. They are called IMF for short, intermolecular forces. It is of absolute importance that you understand the difference between them. Inside means it's the bonds inside the molecule. Outside means it's interaction between two things on the outside. So, how a water molecule affects another water molecule. So, not inside the bonds itself. It we don't do much calculations. We're going to describe what they are and then how they affect the things that we know. So, for instance, you learned forever ago in some class probably that you could float a paper clip on water, right? Maybe if you did it. Okay, it's right. It's because water tension or surface tension, and it's caused by hydrogen being attracted to an oxygen in another water. I have no idea why I went that direction. That was really hard for me to draw. All right, it's because the two water molecules attract to each other. They literally stick together. That's why water forms a droplet. So surface tension is a result of an intermolecular force. All right, it's called what is it called? Hold on. It's a dipole. I don't know why I got stuck there. We'll learn that. But that's the type of intermolecular force that causes that. Intermolecular forces, there's the vocab terms, by the way, there's a lot of them. Hold on. Okay, well, it's just right there. This page printable, sure. It what? You can maybe, actually, you're right. This is on Canvas, but it's, remember how I switched books? I just need to align it. It is there, you just can't find it yet. So, okay, I'll put it on there. All right, so here we go. Unit 7. This chapter deals, the next test is 11 and 13, by the way, and they do relate to each other. If you wonder about chapter 12, don't read it. It's not on the AP test. It's not covered in this class. All right, this chapter deals with intermolecular forces in liquids, solids, and gases. The majority of time will be spent on liquids. All right, so here are the definitions. I will print this out and give it to you tomorrow. I should have done that, but I didn't look ahead. Intramolecular forces are the attractive forces within molecules. These forces are generally referred to as covalent bonds. These forces give molecules their chemical properties. Hold on, let me see how long this is real quick. What time were you out? I don't either. Oh, we got plenty of time. Let me see where this is. I know where to find it. I got to go to my old AP class. Six pages. Let me look at my. Oh, that was close. I've done that before. Okay, I can't hit print until this finishes warming up. Then we'll get it out. Oh, did I do that? Oh, I didn't. All right. These will print. They're going to be 3 pages, which is kind of annoying, but you'll be all right. They're going to be next to each other, and you can fold them, if that makes sense, if I remember right. Nope, I didn't print them that way. So they're going to be huge. Okay, well, all that's printing. I can still talk. Intermolecular forces. They are forces that exist between molecules, not atoms, molecules. These forces determine the physical properties of liquids and solids. So all year, we've been talking about the chemical properties. Go ahead and take that. Now we're talking about the physical properties. So melting point, boiling point, and vapor pressure are typically the things we're going to worry the most about. You all right with that? Did I scare you? All right. The physical state of a substance depends on the balance of the kinetic energy, which is its temperature, of the molecules, and the attractive forces between the molecules themselves. So it's like you go to a dance and you're going to hold on to your date's hand, but the faster the music, the harder it is to hold hands, right? It's just that. So it's a balance between how fast the music is and how tight you can hold on. So in these intermolecular forces, the melting point depends on how tightly they hold each other together. If they hold tight, it takes more energy or more heat or a higher melting point, all right, for things to start breaking apart. I'm just going to randomly grab a pile. Sure, Grace, you're a hero. So it's 3 papers, right? All right. So these forces are definitely dependent on temperature. All right, so the balance of kinetic energy and the attractive forces between the molecules themselves. So if you think about it, why, and like we should easily be able to answer this question by the end of the chapter. Why is salt a crystal at room temperature and water is a liquid at room temperature? Okay, because the way they interact, we need to say it with words from this. All right, water has less attraction or smaller intermolecular forces than salt does. The Na and Cl ions form a lattice structure that sticks to itself much tighter. Now, tighter is a stupid word, much stronger then another water molecule will hang out with itself. Sure, there's an attraction here, and we know it, but at room temperature, that temperature is enough to make it so that they're not stuck, meaning they're not a solid. They interact somewhat, so we call them a liquid. If we were to make it a gas, we would heat it up. If we add heat, that breaks all the attractions. Probably add a paper. No, I had enough in there. I think offset those just in case I grabbed it upside down. Okay, so it's all a balance between these two things and being able to explain them. All right, so this, and it's genius, but this is why the state of a substance can be determined by knowing its temperature. Because every single substance out there will have a certain energy at which it becomes a liquid, where we've given it enough energy that the intermolecular forces are broken a little bit, and now they interact, but not a ton. So if there's still an interaction, but not a really strong interaction, we call it a liquid. There's every solid out there has some temperature at which all interactions can be broken. And then there are no attractive forces between anything, and we call that a what? A gas. We just finished that, right? That whole chapter on that. All right, so these forces determine the boiling point. That's the temperature at which it turns from a liquid to a gas, and the melting point, the temperature at which it turns to a solid. Oh, sorry, from a solid to a liquid. All right. Just keep passing those. Yep, everything feels stapled to me. Thank you for your help. Yep. You look enthused, Soraya. What? Said you look enthused. She's an Arbuckle. They don't do anything halfway. Don't get too down on yourself. That's my job. All right. I think everyone has one, so I just printed too many. Okay. All right. As you read this reader and as you read the book, you can kind of get an understanding of things in your life that you've known, you've experienced, but you never thought it through. Yes. It's what does it look like? That's impossible to describe. It's like it's raining and it's fogging and you're driving through a wall of ice at the same moment in time. It's indescribable. You have all three states that it can exist in equilibrium. And I don't, not super hard, but not super easy. I don't have it memorized. So you need it 0.009 Celsius and around 4.58 torr, which is really, really low pressure. So yeah, you just evacuate it with a pump. We'll get to those. But for now, all right. On the reader, it will have questions like this. I feel like by chapter 11, maybe you figured some things out about me. Where might you see that again? On the test. Wait, really? Like, there's not 100% promise that word for word, but it's basically going to be that idea. If you can answer this question, you can do well on that question on the test. It might be multiple choice. It might be free response.
High pressure,
yeah.
High temperature, low pressure.
Hold on. Every chapter I've showed you almost every multiple choice before. That doesn't mean you pass it though. Absolutely. Absolutely. What are you laughing at over there? Okay, you do whatever you want. I thought you were laughing at me. I've had a rough day, okay? Kids have been laughing at me all day. In general, they've increases the melting point, the boiling point increases. Say it again, Fabian, loud and proud.
Because of how strong the intermolecular forces are, it needs more pressure and heat to separate them.
Don't say pressure. Just say heat. Because pressure would push them together. All right. So the greater the intermolecular force, the stronger they're holding together. The stronger they hold together, the more temperature you need to break them apart. This is not the most complicated thing of the year. Yeah.
What's in like molarity and molality?
Well, that's chapter 13. Yeah, you'll get there, but we're on the front page. You're that kid? You're like, let's see how this ends and go backwards. We'll get there. One is moles per liter and one's moles per kilogram. Yeah, you'll learn it.
There's that word again, in general.
What?
There's that word again, general, in general.
Do you not like that?
No.
All right. There are, and I typed this is my opinion. There are 3.5 types of intermolecular forces. You will read sometimes that there's 4 and sometimes that there are 3. So the one that's a half one is hydrogen bonding. So hydrogen bonding is definitely important, but it's the debate on whether it's officially one of these or not. Okay, just go with me here. These things are absolutely important to know what they are, the application of what they are, when they would exist in something. You have to know those things. So the 3 main types of intermolecular forces are first, ion dipole forces. Now, we talked about dipoles a long time ago. Chapter 8. Does anyone remember what that meant? Do you remember what it meant, Grace? Yeah, there you go. Is that what you're going to say? All right, so water, just real quick. We have water. Oh, I'm swallowing my mask. Hold on, I just got to change. We have water. We know that this is a polar bond, so that leaves partial negatives and partial positives, which are like the sigma things. Does that look familiar? All right, so those produce what we call a dipole. Di just means 2, pole means side. These are less comfortable, but way easier to talk in. All right, so we would say this has a dipole, a negative half and a positive half. Okay, so when we learn about an ion dipole, what we mean is I have a beaker of water. Inside the beaker of water, I have dipoles. Okay, you with me? And that's because, is that spelled right? P-O-L-E? Probably. Yeah. That's because I have a polar substance. You with me so far? So an ion dipole means then I add something ionic to it, like salt. Salt breaks up into Na plus and Cl minus. So an ion dipole interaction is the attraction between the ions, so the sodium plus and the partial dipole minus, and the Cl minus and the partial dipole plus. So they're attracted. So it's kind of weird, like sodium, to separate sodium chloride takes a ton of energy. Or we can dissolve it and it doesn't take that much energy. And that's because this ion dipole interaction. So this is exactly what it sounds like. It is an attraction between an ion and a polar molecule. A common example is salt water. The polar molecules are attracted to the sodium and chloride ions. In order to know the substance has ion dipole, it requires a solution with an ionic substance dissolved in a polar substance. So on the exam, you'll be given a description of something, and it will ask what type of intermolecular forces are present. So if it's going to have ion dipole, you have to have something polar, and you have to have something ionic. So if I said oil and water, you would not put ion dipole because it wouldn't be there. There's nothing ionic in it. Sure, there's dipole, that's the water, but nothing ionic. So as you kind of check down this list, the things in red help you identify whether that thing's going to be there or not. All right. Ooh. No, because oil, yeah, most, like 99% of oils, fats, lipids, all that stuff, they are non-polar and they only have this stuff. Yep. The polarity is based on electronegativity. Okay. Dipole, dipole. Once again, this is exactly what it sounds like. It is an attraction between two polar substances. Now, I'm going to put this big and red here. Oh, it's right here. Never mind. It's already there. It doesn't mean the substances have to be different. So we have two water molecules. They have a dipole-dipole interaction. They don't have to be different molecules. They can be the same formula.
So the last thing, you also have a dipole-dipole.
Perfect. Yeah. In my beaker of salt water, I better say, if it was my salt water, and it asks all of the interactions, you better say ion dipole. You better say dipole-dipole. You better say hydrogen bonding. And then we're going to learn everything has London dispersion forces. So in salt water, they have everything. Now, they vary in how important they are, because really this is important and this is important in salt water, but these still exist. So yeah, they are there.
So like on the AP test, if there were to be a question like this, is it safe to pretty much mark all of them, or?
No, like it is if it has ion dipole, yes, mark them all. But if it has dipole, maybe mark the other two. The only thing I would say is safe to say is there is always London dispersion forces. That was bad English. There are always London dispersion forces. Okay. So these things, in order to be in existence, you have to have a polar substance or two polar substances. And once again, they can be the same molecules. All right, London dispersion forces, also known as LDF, are forces created by induced dipole in nonpolar substances. We'll watch a little video of this tomorrow. London dispersion forces occur when the positively charged nucleus of one atom induces a temporary dipole by attracting the electrons from a neighboring atom. This results in a negative charge on one side of the molecule and a positive charge on the other. These forces exist in all substances and are the weakest of all the intermolecular forces. In italics here, in general, probably a comma there, dispersion forces tend to increase with increasing molar mass. All right, what time did you guys say we're out of here? 04. Should we see how long this video is? It's probably more than 2 minutes. Okay, so that's a little long. We'll watch that at the start. There's tons of stuff on the internet about this. I have an Ed puzzle I would like you to watch. It's 5 minutes. and I foreshadowed it. All you have to do at the end is say yes. You just have to watch it, and type yes. All right, so we'll watch that. London dispersion forces are a little bit weird. It's like when you pull two magnets together and they're opposite charges, you can feel them push each other apart, but there's not really, they don't stick. The one kind of influences the other. In a London dispersion force, we have the nucleus of one, the nucleus of the other, and this one causes an attraction for all the electrons. So now this, all the electrons go to this side, and we have a negative side. That leaves the nucleus exposed over here. So then we have a positive side. Now, these don't last long at all. Like they're almost an instantaneous, they're there and then they're not there. But if you have trillions and trillions and trillions of atoms that are constantly going through this, you can have small attractive forces. Those are what give some things that are nonpolar their properties. Now, the larger the molecule, the more important London dispersion forces are to its physical property.
Because does it last longer when they're larger molecules?
It happens more often. I wouldn't say it lasts longer. It just happens more often. So you get a greater pull. Okay, hydrogen bonding is a very strong form of dipole-dipole bonding. That's why sometimes they don't say it's the third one. Hydrogen bonding exists only between hydrogen atoms bonded to F, O, and N. This is super important because you just might think, well, if it has hydrogen, we're ready to roll. But that is not true. Hydrogen must be with one of these three things. Hydrogen bonding accounts for the unique properties of water. So yeah, some books say it's the fourth one. Some don't name it as a specific one. So that's why I call it a half. Please watch that video tonight. If you need to finish the test, please come today after school.